Bismillahirrahmanirrahim. The topics selected for today's lecture are positive definite matrices, leading principal submatrix, and the Cholesky decomposition. First of all, we will study the definition of the positive definite matrices. In matrix, A is positive definite. Matrix A is positive definite if it is symmetric. You are very well aware of a symmetric matrix. And if A is symmetric and holds this inequality, which is x transpose A x greater than 0 for every n-dimensional vector x which is not equal to O. Now we consider x transpose Ax. X vector is mentioned here. This is the x vector, while this is the transpose of the vector x. Here A is a matrix which is symmetric and has n dimensions. We get its solution. We will multiply this matrix with this vector first, and solving this matrix and this vector, we obtain this result, which is written in summation form. And after this, we multiply this row vector with this vector, and we obtain this one identity, which is written in summation form here. We can easily check that what this entry or component behaves. We can see, is it positive or negative, is it greater than 0 or less than 0 or equal to 0. And the definition shows that a matrix A is positive definite if it is symmetric and x transpose Ax is greater than 0. If this is greater than 0, then matrix A is positive definite. We consider the example. Here A is a 3 cross 3 matrix. We have to show that this matrix is positive definite. We observe that this A matrix is symmetric matrix because its transpose is equal to the given matrix A. We consider this expression x transpose Ax. X is a vector of dimension 3. Its dimension depends on the dimension of the matrix A, and this is the transpose of the vector x. We know that how we have to multiply these three matrices. We will first take the result of the product of these two matrices, this matrix and this vector. We obtain a vector after multiplying the matrix with the vector. Now we multiply this row vector with this column vector, and we obtain this entry. This is one entry. Now we have to show that this is positive. In this expression, we cannot suggest that it is positive or negative because these are five terms which involves negative sign and positive signs, and we cannot say about x1 x and x2 or n about x3 that these are positive or negative. We have to rearrange these terms in such a way, and later on we conclude that the above result can be written in this form. Now x1 square, one term which is definitely positive term because it's x1 has its square, and this term is also positive. This term is also positive. Similarly, this term is also positive, and the sum of all the positive terms is always positive. The this result is greater than 0 unless x1, x2, x3 all are equal to 0. Hence, we conclude that the given matrix is positive definite. The statement of the theorem says that if A is positive definite, then A is non-singular. We know about the definition of the positive definite, and we are also well aware of singular and non-singular matrices. We will prove this theorem by contrapositive form. And for this, we will consider that A is singular, then A is not positive definite. This is called the contrapositive form, while our statement is that if A is positive definite, then A is non-singular, and the contrapositive form of this statement is if A is singular, then A is not positive definite. Assume that A is singular. If A is singular, then a theorem says that for any non-zero y which belongs to Rn, any non-zero vector which belongs to Rn such that Ay is equal to 0, we can obtain such result where A is singular matrix. If we can obtain this result, then definitely we will obtain this result. And this result shows that A is not positive definite. Hence proved that if A is positive definite, then A is non-singular. Another definition, a leading principal submatrix of a matrix A is a matrix of the form AK, which is given here, where K lies between 1 and n. A is a matrix of n cross n orders. AK is a submatrix where K lies between 1 and n. Then this AK is said a leading principal submatrix. Theorem related to the above matrix, a symmetric matrix A is positive definite. Symmetric matrix A is positive definite if and only if each of its leading principal submatrix has a positive determinant. A symmetric matrix is positive definite if and only if each of its leading principal submatrices has a positive determinant. Now it is another way to show any matrix is positive definite or not. We will consider the submatrices of the given matrix, leading principal submatrices of the given matrix, and we will prove that it has positive determinant or not. We again consider this example, which we have already proved that this A is positive definite. In the light of the given theorem, we will again show that A is positive definite. It is important to note that it, it has three principals, leading principal submatrices, because K lies between 1 and 3, including 1 and 3. You will get A1, A2 and A3. Determinant of A1 is determinant of one entry, which is 2 and greater than 0. A2, you will calculate the determinant of this matrix, which is 3, and again it is greater than 0. Similarly, the largest leading principal submatrix, which is the whole matrix, because K is equal to N here. Simplifying, we obtain that 4 is greater than 0. Therefore, we conclude that the given matrix is positive definite. A result, if A is positive definite, then linear system Ax is equal to B has exactly one solution. We will keep it in our mind that if A is positive definite, then the system Ax is equal to B will have exactly one solution. Next theorem, let M be any n cross n non-singular matrix, and let A is equal to the product of transpose of M with M. Then A is positive definite. First, we must show that A is symmetric, because it is important for the proof of a positive definite matrix that that matrix should be symmetric matrix. We recall the elementary formulas. We know that this result holds. If we want to take the transpose of two matrices, the product of the two matrices, the two matrices will be written as C transpose B transpose. Similarly, the transpose of the transpose of a matrix is the same matrix. We find that A transpose is equal to this, and using these two results, we obtain that A transpose equal to M transpose M, which is equal to A. Hence proved that A is a symmetric matrix. Next, we must show that this inequality holds for all non-zero vector x. For such x, we have x transpose Ax is equal to x transpose. Replace here M transpose M on the place of A. Let y is equal to mx, so that y transpose is equal to this. then X transpose AX is equal to Y transpose Y, because X transpose AX, X transpose AX is equal to this, and we say that Y is equal to MX. Here we will write the Y, which is written here, and it is the Y transpose. Therefore, X transpose AX is equal to Y transpose Y, and we obtain this result in the form of an entry, which is yi square. The sum of squares is certainly non-negative, and it is strictly positive if y is not equal to 0. If y is not equal to 0, then surely this sum will give us a positive result, and it is clear that y is equal to mx is not equal to 0 because m is non-singular and x is non-zero. Thus, we obtain the result X transpose AX is greater than 0 for all non-zero X, and A is positive definite. Application of the last theorem can be seen in these two examples. In first example, M is given here with 4 entries, 1, 2, 3, 4. This is given are non-singular. M is non-singular because its determinant is equal to -2. We can obtain A, which is the product of M transpose M with these 4 entries 10, 14 and 14, 20. This is positive definite. Similarly, if we take M in this form, then M is non-singular because the determinant of matrix M is 1. We obtain A as the product of these two matrices, which is a 3 cross 3 matrix. This A matrix is also a positive definite matrix. You can check the leading principal submatrices, which says that the A1 is positive, later on A2 is positive, and you can check easily A3, which will also be positive. Similarly, in first example, A1 is positive, and then A2 is also positive. The leading principal submatrices shows that these matrices are also positive definite, and this, according to this theorem, these both examples shows that A is positive definite matrix. Next, our topic is Cholesky decomposition, and this theorem is related to the Cholesky decomposition. Statement of the theorem says that let A be positive definite. A is a matrix which is positive definite. Then A can be decomposed one way into a product of R transpose R. This is called the Cholesky decomposition. What is R? R is an upper triangular and has all main diagonal entries are II positive. R is called the Cholesky factor of A. A is a positive definite matrix which can be decomposed in two matrices, the transpose of R and R. and all entries of the main diagonal are positive. And this R is called the Cholesky factor of A. Let us consider a matrix A, and R is this. All its diagonal entries are positive. R is a triangular and has positive main diagonal entries. We can also check that A is equal to R transpose R. Therefore, R is Cholesky factor of A. Let's see the decomposition of the matrix A. R is a triangular matrix which is on the right side of the right hand side, and this is the R transpose. The elements Aij of the ith row of R transpose with the jth column of R. Nothing that the first row of RT has only one non-zero entry. First row of RT has only one non-zero entry. We focus on this row. If we make a relation of the corresponding entries, we will see that A1j will be equal to the sum of these products. In particular, when j is equal to 1, we will have A11 is equal to R11 square, which is the first entry. And we can easily obtain R11, which is the square positive root of A11. We know that the positive square root in the right one because the main diagonal entries of R are positive. We know that R11. We can use the equation A1j to calculate the rest of the first rows of R. This is the formula to obtain all the entries of the first row R1j, because we know that A11 R11, this value is calculated, and A1j are given in the main matrix of A. We can easily obtain R1, 2, R1, 3, R1, 4, and so on up to R1, and we can easily calculate all the entries of the first row of R. This is also the first column of R because RT is the transpose of R. So all the entries of the first column of R transpose can be gained by this formula. We next focus on the second row because the second row of R transpose has only two non-zero entries. If we compare the entries and make a relation between the entries of the second row, we obtain this relation. J will vary, and we will get, first we will deduct another relation, R2j. We will calculate R2j first because only element from the first two row of R appears in this equation. In particular, when j is equal to 2, we have A22, which is R12 square plus AR22 square. R12 is already known. Therefore, we can calculate R22 in this way. Once R22 is known, The only unknown left is R2j. Thus, we can use 1.4.11 to compute the rest of the second entries of the second row by varying j from 3 to onward. We can get R2 3, R2 4 and so on by this relation. No need to calculate R21 because R21 is 0. We know that the first two rows of R. Now, as an exercise, you can show how to calculate the third row of R. Now, let us see how to calculate the ith row of R. Any row of the R is under consideration. We see how can we calculate the entries of the ith row of R, assuming that we already have first I minus 1 rows. If we have I minus 1 rows, we can calculate ith row of R, since only the first I entries in the ith row of R transpose are non-zero. Therefore, Aij is equal to R1i R1j plus R2i R2j. This relation will help us to calculate any entries of the row of R matrix. All entries of R appearing here lies in the first I rows. Since the first I minus 1 rows are known, the only unknown in this relation are Rii and Rij. Taking I is equal to j, we obtain this relation. Which we can solve for Rii. We want to calculate Rii with this relation. Now we have Rii, we can obtain Rij with this relation. We don't have to calculate Rij for j less than I because these all entries are 0. Here is an exercise. A matrix is given. We have to prove that A is positive definite, and in the part B calculate the Cholesky factor of A. You have to calculate the R matrix. In C part, find three other upper triangular matrices R such that A is equal to R transpose R. And in fourth part, let A be any n cross n positive definite matrix. How many upper triangular matrices are such that A is equal to R transpose R or there? This is the Cholesky algorithm. When you will calculate all the entries of Cholesky factor R, you will understand this algorithm. Here you can write this arrow sign Aij is equal to, and here you can replace the equal sign if you want, also here and at this place. Try to understand this algorithm. Cholesky decomposition is useful because R and R transpose are triangular matrices. If R is triangular matrix, then R transpose is also a triangular matrix. Suppose we wish to solve the system Ax is equal to B where A is positive definite. If you want to solve such system where the coefficient matrix A is positive definite, and if we know that Cholesky factor R, we can write the system as R transpose R at the place of A. The system will be converted in this form. Let Y is equal to Rx. This Rx is named as Y. Then we will have R transpose Y is equal to B. It is just like the simple decomposition method we have already studied. Now we have two systems Y is equal to Rx and R transpose Y is equal to B. Y is unknown, so therefore we will solve this system, and later on we will go to solve Y is equal to R of X when Y will be known, and we will calculate X later. Hope you will solve the Cholesky decomposition method. Here a matrix A is given and a vector B is given. We note that A is symmetric here. Everyone is aware of the definition of a symmetric matrix. We will use Cholesky method to show that A is positive definite. And calculate the Cholesky factor R. We will use the Cholesky factor to solve the system Ax is equal to B by forward and backward substitution. These values are calculated in Cholesky decomposition process, that R11 is square root of A11 and A12 will be calculated as A12 by R11 and so on. All the entries of the R matrix will be calculated here. Thus, R, which is the Cholesky factor of the given matrix or the given system, is calculated here. Since we were able to calculate R, A is positive definite, we can check our work by multiplying R transpose by R and seeing that the product is A. Now next, to solve Ax is equal to B, we first solve this system and obtain Y, which has these values. Next we will solve the system Rx is equal to Y. By backward substitution we will obtain the value of the vector x, which are which is our desired vector. Finally we check our work by multiplying A by X and seeing that we get B. The factor the positive definite matrix A into L transpose where L is lower triangular. The same thing is given here. Determine the Cholesky L transpose factorization of the positive definite matrix A. A is a positive definite matrix. We will calculate the matrix. The L transpose factorization does not necessarily has ones on the diagonal of the lower triangular matrix L, so we need to have A as in the given form. If we multiply these two matrices, we obtain this one matrix, and we obtain all the entries of A of the L. Then the entries of the L transpose will be automatically calculated. So this is the form of A in terms of L transpose.